Hi guys, it's Kate, and this is a sample problem of Stokes' theorem from our worksheet in class today. And I thought it's a pretty interesting problem. There are a lot of different things at hand going on here. It recalls many different topics that we've studied over the course of the semester, and it's a great piece of review. It's also very similar to one of your homework problems, so it's certainly useful, especially if some of the things that you need to recall, like parameterizing surfaces or parameterizing space curves or integrating surface integrals, are a little bit rusty. It might be worth going through step by step. So let's get started. What we're told is that we have the plane z equals x plus 4. That is this light blue plane right here. And it intersects the cylinder x squared plus y squared equals 4, this pink cylinder. And it intersects the cylinder in a curve C, which I've made lime green for the purposes of being able to see it much better. This solid part of the curve is what's closest to us. This dotted part of the curve is going to be on the back side of the cylinder over here, but behind the cylinder. And it says that suppose C is oriented counterclockwise when viewed from above. So when we look down, we should be looking down at a counterclockwise orientation for C. So I'm going to add that on here. That's going to look like this. So that's the direction that C would be seen as counterclockwise from above. It says let F be the following vector field here, and our job is to evaluate this line integral, F dotted with dr. Now, right off the bat, you're probably thinking, if I was to compute this from the definition, well, this is some sort of circular path, so that would involve sine and cosine in x, y, and z, because z is also going up and down. Z is being controlled by x plus 4, and x is going to be cosine t, or 2 cosine t in this case. And oh my goodness, when I compose f with this parameterization and I dot it with r prime, that's going to be a crazy integral for me to have to evaluate. And of course, the whole idea behind Stokes' theorem is that you don't have to evaluate that integral. What you're going to do is exploit Stokes' theorem, which is the following. And instead of computing this really complicated line integral, we're going to compute the surface integral of the curl of the vector field over the surface whose boundary curve is this boundary C. Now, of course, the first thing that we need to figure out is what is this surface? And as we discussed in class, the surface can be any surface whose boundary curve is this boundary C, and we want to pick the one that's easiest for us. So we could say, oh, the surface S is the cylinder that gets cleaved like this. And sure enough, if you had an infinite cylinder here and you had a boundary curve here, that could be an example of that. But we're really looking for the simplest possible surface whose boundary curve is this ellipse. And in fact, what it's going to be is the portion of the plane z equals x plus 4 bounded by this ellipse. And it ends up looking like a little disk. So let's take a look. So I've colored it in dark blue over in the picture. Again, it is the portion of the plane z equals x plus 4 that's bounded by C. Now, in order for us to even compute this surface integral, the first thing that we need to do is parameterize this surface right here, this disk. And since this disk is part of the plane, z equals x plus 4, that's what we're going to use as the basis for our parameterization. Z is already written in terms of x, and y will be the other parameter. Let's write this down. So we have u as the x component function, v as the y component function, and u plus 4 is the z component function. You may already be wondering, well, what are my parameter bounds? Remember that our parameters u and v are just x and y. And of course, if you look at this disk and its shadow in the xy plane, it fits entirely inside this cylinder of radius 2. So we know that x squared plus y squared, or in terms of our parameter names, u squared plus v squared, has to be less than or equal to 4. Now our next chore is to see whether our parameterization maintains the appropriate orientation necessary for this particular surface. And of course, we weren't given an orientation for the surface in our setup for this problem. We were given an orientation for the curve. And remember, for Stokes' theorem, what this means is that if we're traveling that boundary curve C, so that we're left-footed, which means we're walking around this lime green curve so that our left foot is in the region. then our head will be pointing in the direction of the normal vector. For us, this means that our normal vector needs to be pointing upward. Again, this means that if we were a person walking around this lime green curve, and already the lime green curve, we are told, must be traveled counterclockwise when viewed from above. So if we are moving counterclockwise and we need to be left-footed, that means we're going this way. Our head will be pointing in the direction of the normal vector. So we will be standing on this like so. And sorry, I can't really make this light blue plane transparent, but you understand that we are standing up here on this disc and moving down and around towards the back of the cylinder and then coming around the back and up towards the front. We're moving counterclockwise when viewed from above, so we're matching the orientation of the boundary curve. And in order for us to be left-footed, our head is pointing upwards, which is in the direction of the normal vector. So we need to see now whether our parameterization gives a normal vector that is correctly pointing upwards. Again, we compute RU, RV, and then we cross them to get the normal vector given by our parameterization. Sure enough, that normal vector has a positive z component, so it is in fact pointing upward. And remember, when you're looking at this plane, there are in fact two normal vectors at any given point. There's one that's pointing like this and one that's pointing like this, straight through the plane. We are interested in the one that's pointing in this direction, not in that direction. So we want this guy. Again, to even double check and make sure that that makes sense, recall that when you put all of the variables on one side of a plane equation, the coefficients give you the components of the normal vector. So the coefficient on x gives you the x component for the normal vector. The coefficient on y gives you the y component for the normal vector, so on and so forth. So we can see that the normal vector is some multiple of -1, 0, 1. In order for it to point upwards, we do want that z component to be positive. So that's another way of double checking to make sure that that normal vector does make sense, that we computed it correctly. All right, we're all set. Our parameterization of this surface here preserves orientation the way we want it to. Now let's take a look at using this parameterization and composing the curl of f with that parameterization. So first things first, let's figure out what the curl of f is. Here's the curl of f, and I seriously just computed it from f up here the old-fashioned way. So the curl of f is -1, -1, -2. We're now going to compute the surface integral. So the curl of f dotted with ds, which is our normal vector, -1, 0, 1. And then we're going to integrate it over S. And remember, integrating over the surface once you've parameterized the surface is integrating it over our parameter bounds, which means we're integrating it over this region, u squared plus v squared is less than or equal to 4, or a circle of radius 2 in the UV plane. Let's take a look at what this ends up being. Here we have the curl of f dotted with the normal vector, and it ends up being the double integral of -1 over the region u squared plus v squared less than or equal to 4. Now there are two things that you could notice. You could either remember to yourself, oh, whenever I integrate 1 over any particular region, I get the area of that region. Of course, the area of the region where u squared plus v squared is less than or equal to 4 is going to be, remember u and v are just x and y, so it's going to be -1, because we have a negative sign here, times the area of the circle of radius 2 in the xy plane. So you could quite simply just write down, oh, it's -1 times the area of a circle of radius 2. In which case you're like, -4 pi, yay, I'm done. Maybe you forgot that particular piece of information, and instead you thought to yourself, well, u and v are like x and y, and so the region in the plane that I'm integrating over, u squared plus v squared less than or equal to 4, looks something like this. Right? A circle of radius 2 in the uv or xy plane, since we just used x and y as our u and v. And what skills did we learn this semester about how to integrate over a region that's a circle in the plane? Well, we can certainly use polar coordinates. Just sub in r cosine theta and r sine theta everywhere we see u and v respectively. And instead of du dv, which are really dx dy, we want to plug in r dr d theta and then have our parameter bounds be in terms of r and theta. So this could just transform into converting this from Cartesian, because u and v were in terms of x and y, into polar coordinates where every single u in the integrand, which there were none, but u turns into r cosine theta, v turns into r sine theta. But what's important is that u and v, which were x and y before, that used to be u squared plus v squared, is less than or equal to 4. Now we can describe that as r goes from 0 to 2, and theta goes from 0 to 2 pi. So our integrand becomes negative r dr d theta. Remember, when we convert to polar coordinates, we have to go from Cartesian to polar. So there is a factor of r that goes in there. The bounds for r goes from 0 to 2. The bounds for theta go from 0 to 2 pi. And that is still negative 4 pi. This particular transformation is quite useful in many problems. And you'll see some other examples of that as you look through the solutions for the worksheet. But certainly try them on your own, give them a whirl. Remember that the main steps are always the same. First, the integral that a Stokes theorem question will ask you for is never what you should compute from the definition. This line integral is nasty. Instead, I want to compute the surface integral of the curl of the vector field over the surface. What do I need to do? Well, first, I need to take my curve and find that surface whose boundary curve is C. Once I have that surface, I need to parameterize it. I then need to see if the normal vector that my parameterization gives is pointing in the right direction. How do I do that? Well, I'm already given a curve C that has an orientation. I think to myself, if I'm traveling in that direction around the curve and I'm left-footed, which direction is my head pointing in? The direction of the normal vector. In this case, our head is pointing upwards, so we're looking for a normal vector with a positive z component. We get that, so our parameterization is perfectly fine. Then we go back to our original vector field and compute the curl of f, because that is what we are taking the surface integral of over this surface. We find that the curl of f is -1, -1, -2. Note that if there were any variables left over here in the curl of f, we would need to compose the curl of f with our parameterization. But since these are all constants, there's no composition that needs to be done. We take our curl of f and we just compute the surface integral very straightforwardly. The hardest part is parameterizing the surface, making sure that your parameterization generates a normal vector that is pointing in the correct direction. The rest of it is just exactly the surface integrals that you did over the weekend. We have our curl of f here. And do note that this should say less than or equal to there. Curl of f dotted with ds, which is our normal vector. We want to integrate over our parameter bounds, which happen to be, remember u and v were just x and y vary over a circle of radius 2 in the xy plane here because they fit inside that cylinder that is x squared plus y squared equals 4. Once we dot that, we've simplified this down very nicely. Maybe you have a moment here where you remember that integrating 1 over any region gives the area of that region. So integrating -1 will be -1 times the area of a circle of radius 2 in the xy plane. But maybe you forgot that and you think to yourself, integrating over a circle of radius 4 is really difficult. You can convert this into polar coordinates. Remember that du dv, because that's really dx dy, becomes -r dr d theta. And then r bounds are from 0 to 2, theta bounds are from 0 to 2 pi. And either way, once you compute, whether you get the shortcut of thinking, oh, this is -1 times the area, or you convert and do it out by hand, you will get -4 pi as your final answer. And that is computing this side of Stokes' theorem, but of course, this is an equality. So this is the value of this line integral. If you have any questions, please don't hesitate to ask.